In the previous unit, we were looking at permutations, which required us to look at organized counting. In this unit, we're moving into combinations where we are not looking at organized or ordered items. So we're going to start with permutations with non-ordered elements. So combinations are very similar to permutations, just order doesn't matter. So we'll take a look at some examples here. In our first bit, we're looking at situations where we have a permutation, but some of the items involved in the permutation are identical. And so if we have identical items, the order that we put them in doesn't matter, and so we have to take that into consideration and remove that from the possible number of permutations. So what we do to do that is we divide by the number of ways you could arrange that number of items, or that number of items factorial. So this is our formula here, and we'll take a look at it with an example of fridge magnets. So if I have these fridge magnets here, and while my drawings may not look exactly the same, if you had fridge magnets that were these letters in same colors, they would look exactly the same. So given these fridge magnets, how many ways can they be ordered? Well, we have 6 fridge magnets. If they were all different, the number of arrangements would be 6 factorial. However, we have 2 red A's, and wherever we put them, we won't be able to distinguish one from the other. So we can arrange 2 red A's in 2 factorial ways. And then we have 3 black C's, and again, we wouldn't be able to distinguish them from each other, so that's 3 factorial ways we could arrange them. We got to get rid of that. So if we work this out, 6 factorial is 6 times 5 times 4 times 3 factorial. Divide that by 2 factorial times 3 factorial. I'm going to change that. Sorry, I'm going to expand that 2 just to show you. 2 times 1 times 3 factorial. 3 factorials will cancel. The 2 will cancel with the 4 to leave that as a 2. So we actually are left with 1 and 1 on the bottom here. So it's 1's on the bottom. 6 times 5 times 2, that's going to give us 60 different combinations of the letters on the fridge. So again, we looked at the total number of permutations divided by the permutations of each of the repeating letters, repetitive letters. In the next situation here, we have the school's postal code P6A5K9, and we want to know how many ways we can arrange the postal code if the numbers cannot be reordered. So the 6, the 5, and the 9 can move from their current positions, but they can't be put in a different order. So we can't have the 5 appearing before the 6 and so on. So what we do in these types of situations is we just treat the numbers as if they were all the same number. Let's treat them as if they were identical items because we can't rearrange them. And there's only one way to keep them in that arrangement. So the total number of arrangements without any restrictions would be 6 factorial. And then with our letters being rearranged, but the numbers not the 3 ways you could arrange the numbers would be 3 factorial. Or sorry, there's 6 ways of arranging numbers, but there's our arrangements. So 6 times 5 times 4 times 3 factorial over 3 factorial. Cancel the 3. 6 times 5 times 4 is going to give us 120 different ways of arranging those items. So again, given the identical items, we divide out the permutations for the individual identical items. In the case where something can't be reordered, then we treat them as identical items, and we then divide out the number of arrangements of those identical items.